I guess we should get started then. Thank you, everybody. Welcome back. This is lecture 3. Seems that time goes very quickly when you have only one lecture a week. Everybody, can everybody see the slides?
Yes.
Slides are fine. Okay, so welcome back. This is lecture 3. Today we're going to do SIR models. There was a homework problem introducing the concept. We uploaded a PowerPoint, a PDF of this Brouwer Mathematical Models in Epidemiology textbook, which is quite good. This is chapter 2, section 4, primarily, that we're going to be talking about today. I wanted to make a few comments on the homeworks. Some people put a lot of effort into the homework. A few people didn't send me homeworks. So if you intended to send me a homework and you didn't get a grade on it, please check and either email it to me or upload it into Canvas. And there are 1 or 2 people who didn't do the computer problem. And again, I don't know if that was intentional or not. So if you decide you're not going to do a problem in a homework assignment, that's fine. But let me know, so that I know you didn't do it intentionally rather than that it's missing. People found some very interesting papers, starting after people have done their preliminary review of things for the projects. I would like to, not every week, but periodically have people suggest papers, and then together have us all prepare them and then work them up in class to actually develop a model of replication of the model in class. Somebody found a very nice model of infection dynamics, population infection dynamics, and talked about it in their homework, first homework. And it would be, for example, a very good problem to do in class together if they decide not to do that as a class or project for the semester. When people do find papers, it's very helpful to give a formal citation, year, authors, and so on, because sometimes the title of the paper is unique. Sometimes the title of the paper is insufficiently definitive for me to figure out which one you're talking about. So please do that. Another thing that came up is something that I often would talk about in the first lecture, but seemed a bit abstract, and so I didn't mention it, which is that when you see the word model, it can be a source of some confusion because different domains use the word model in different ways. Experimental biologists use the word model in 2 different ways. One of them means any experimental system that's not a human being. So a mouse model of disease X, an in vitro model of disease Y. And so just because the word has model, the paper has model in its title, doesn't mean that there's actually any modeling of the kind that we're talking about. Sometimes model is also used in a way that's a little closer to what we are talking about here, which would be what we would call a conceptual model, which is, does interleukin 6 antagonize or promote interleukin 12? That would be a model of the role of interleukin 6. And so both of those things are not totally unrelated to the kind of mathematical conceptual modeling we do, but are not the same. And bioinformaticians often use the word model to mean anything with statistics in it. And so bioinformatics papers will often have the word model in them when they don't actually have any modeling of the kind that we're talking about. And so if all you're going on is the abstract of a paper, you need to be careful, because the word model showing up in an abstract does not necessarily mean there's any mathematical modeling or computational modeling in the paper. So I wish there were, sometimes searching on computer simulation rather than model is a safer way of finding a modeling paper. Although sometimes the bioinformaticians will even use computer simulation to be doing statistics. So that's something that one is to be aware of. But in general, I found people came up with some very interesting papers and thought quite well about these problems. We'll have plenty more opportunities to work on that. So, and if people need to hand things in late, let me know. I wanted to discuss a little bit about the plans for the next week or two. This week, I'm going to do SIR models and maybe do a simple extension, depending on how time goes. We're going to spend a little bit more time this week doing in-class exercises than I might in the future, because I think it's really important that everybody be able to get the computing working. And once I'm confident that everybody's able to do the computing successfully and they're comfortable with it, then we can kick more of that to being done on your side offline. But at least to begin with, I think it's pretty important that we do these exercises together, make sure everybody's on the same page. And so that's, I don't know exactly how far we'll get today, but I'll do my best. So that's the plan for this week. And that one's not really very much up for discussion because it's already written. For next week, I was going to do what are called SEIR models. That's what Josh and I were chit-chatting about before class started. SIR models assume that you're susceptible, infected, or recovered. SEIR models are susceptible, exposed, infected, recovered, which means that you don't get sick and become infectious right away. And that's true of many diseases, including COVID. Probably for the first day or two after you've been exposed, the virus hasn't replicated enough in your body that you're able to infect anybody else. They're more complicated models with longer names where you have other states. We probably will do a little bit of what are called SIS models, which are where you get your ability to get sick again immediately after you've recovered. And you could have SEIRS models, which would probably be a better representation of how COVID works, which is you are susceptible, you're exposed, you're infected, you get better and you're resistant for a while, then you become susceptible again. You could add a fourth compartment, which is probably even better for COVID, which is SEI1, I2 or Q, and then R and S, in which case you're susceptible, you're exposed but non-infectious, you're infectious and feeling okay, so you're running around infecting other people, and then you're quarantined and still sick. So you're not infecting other people, but you're still sick, and then you're recovered and resistant for some time, and then you go back to being infected. We don't really know yet about the latter part because we haven't had enough time to be able to do that. So I want to do that, and I want to introduce parameter fitting. We'll do a teeny bit of parameter fitting this week, courtesy of Josh is helping us, but in a very by hand, not by computer. And then next week we will do some actual parameter fitting. And we'll discover that parameter fitting isn't so much fun, but it's part of life, and so we have to get used to it. And then my hope would be that if people have a suggestion for a SEIR type model paper from the ones that we've been looking at or elsewhere that we would like to replicate together, we could try that, especially if it's paired with experimental data. And then after that, I would move on to in-house dynamics models and spend a couple of weeks on that. And then do PBPK and departmental models. And then we potentially have a couple of weeks, depending on how things go, where we could do other things. And so your suggestions about balance and what you'd like to add or take out of that are welcome. So does that seem like a reasonable rough agenda? We can always adjust it, seeing how fast or slow things are. But if people have objections or suggestions, people seem to think that that's okay. Great. People are welcome to talk to me offline about these things as well. But I would like to try to do at least 1 week where we work together to replicate epidemiology paper result, and 1 week where we try to do a within host dynamics result together. I think that's the most interesting thing, is to try to do it together to figure out how it works. Okay. So the class 3 topics are pretty simple. We're going to talk about SIR models of epidemics. Not exactly sure what the question mark was there for. And I'll introduce very briefly the concept of fixed points. It's a little bit hard to talk about fixed points without talking about stability, but we'll do that. People will have to remind me let me give you, I want to give you a heads up. I guess that's why the question is there, which is if you haven't played around with simple matrix manipulation, and if determinants and eigenvalues are things that you learned in the past but haven't worked with for a while, I would ask you to look up somewhere and quickly refresh yourself about how to determine, calculate determinants and eigenvalues, what an eigenvalue is. When you're going to do stability analysis of linear systems, like the ones we're working with, first ordinary differential equations, you determine stability by calculating the eigenvalues of the Jacobian matrix of the system of equations. Typically, if we're going to do it by hand or on slides, we don't do more than 2 by 2 matrices, which are pretty straightforward. But conceptually, these apply to arbitrary dimensionalities. And so if eigenvalues and eigenvectors are things you need to refresh, I'll try to cover it in class, but I won't be able to spend an enormous amount of time on basic linear algebra. So I encourage you to refresh yourselves on that. I won't assume that people have done linear stability analysis, but I will assume that if I write a 2 by 2 matrix and ask what the eigenvalues are, that doesn't cause an issue. And the reason I'm not doing fixed point stability this time is because I want to make sure that people have time to remind themselves of that. Okay, so last time we wrote down this very simple SI model where we had susceptible individuals and they became infected. And we said that the fraction of the population that was infected was the number of infected divided by the initial total population, which is called S naught. We wrote down a probability of becoming infected per encounter with somebody else, which was a gamma times the probability that the person that you were encountering was infected. And we said that there were n encounters per day. And really, if I'm going to do that properly, I should use a Poisson relationship, but I didn't. I'm assuming it's small. And that product n gamma, which I've broken out separately, is often called beta in the literature. And unfortunately, the notation that everyone uses is slightly different. So in that Brouwer textbook, the notation and the naming of the parameters is somewhat different from the ones in Murray, which are somewhat different from the ones in Britain. And they're somewhat different from the ones that I started out with as well. All right. And so I would like to start out by just going back to that very, very simple model that we did before, that SI model lecture 2 exercise 1, and I want to not plot the rate of the total number of people infected, but I want to plot the rate of new infections. And it's worth saying that the rate of new infections is the slope of the number of people infected. Okay. So I'm going to resize my screen here. I should get rid of this email. Should be no reason my email should be on the background here. And so I'd like everybody to open up okay. And I did not have time. I'll set up a poll asking people for, while people are working, I'll set up a poll asking for people if they're done or need more time on the exercise. I don't think I have the polling available. Not sure why not. Oh, there it is. Maybe. Let me see. Yes, it is there. All right, I do have it. Okay, great. All right, so does everybody have this? Is everybody able to find that old model? I guess I can try my poll. Somebody said yes. Okay, good. So one thing to remember is how do I plot the rate of new infections rather than the amount? Do people remember how to select columns in Tellurium? I'll do it with you. We'll just do it together. So if I name a reaction, the name of that reaction E1 gives me the rate law on the right-hand side. That's why I name it. So if I go in here and do m.simulate, and I now do square bracket time.
James, we're still seeing your PowerPoint.
Oh, okay. I'm sorry. Thank you for that. Is sorry about that. So I wish somebody should catch me sooner on that. Thank you. Sorry about that. Do you want me to step back? So please go to Jupyter Notebooks on Tellurium. Open SI model lecture 2 exercise 1, which is what we had here. Okay, so I'll give people a second to do that. Thank you, Josh. Are people, I guess I can ask. But now it puts that on the wrong. If anybody's having trouble getting into NanoHub and getting Tellurium launched, please let me know. So what I need to do is I need to plot E1, and to do that, some of these things it's always good to look them up. You can always refer to the the documentation, that tellurium documentation, which is very good. Something, and there's also those cheat sheets that I distributed. But after in the simulate function, I put in a pair of square brackets and then time, and then the name of the parameter, the variables that I want to plot. In this case, the variable I want to plot is E1, like that. And I hit control, run, and there we go. That gives me basically the derivative of I. Not just basically, it is a derivative. Another thing that's sometimes useful, there are lots and lots of options for plot functions. Most of the time I'll have it turned off. Sometimes if I want to see things more clearly, a useful one to remember is, and again, you can look them up, is grid equals true. And that gives me some grid lines. Makes it easier to reference things. Okay. So that was the or did that work for people? Okay. All right. So that's what we got. Not a very sophisticated plot. And now I want to remind you of something that we talked about last time, which is how to look at results. And so I said to always start looking at what happens at small values or small times. And so if I look at this plot, at time 0, my value is essentially 0. And the slope is essentially 0. And it stays small and 0 for quite a while, for about 7 days before much happens. And then I said the next thing to do is to look at long times. And at long times, the value is decreasing, and the final value is essentially 0 again. And that's happening around 20 days. And then I say look at intermediate times. In this case, the system isn't monotonic. I go up and then I go down. And so if I see something like this, the natural things to ask about it are, what time is the peak? How big is the peak? Here, the peak happens around 14 days. The value of the peak is somewhere around 250,000. And the other thing that's going to be important that we're going to talk about a lot today is the peak symmetrical or not? Is the upslope and the downslope the same or not? And in this case, they are. If I took a mirror around my maximum, they would be essentially indistinguishable. So that's about all the information I can get out of this. Okay.
I have a question about sigmoidal curve shapes.
Yes.
So in the graph that we see here for the SI model that plots the curve for infected individuals and uninfected individuals,
Yes.
the curve for infected individuals is a sigmoidal curve. Is the curve for uninfected individuals also called a sigmoidal curve? Because it's like
Yes.
the same shape but reversed.
Yes. So you call I an increasing sigmoid and S a decreasing sigmoid.
Okay, thank you.
So that's absolutely a good question. And sigmoids come in all sorts of flavors. For example, here it looks very symmetrical, but if we were in a logarithmic scale, and sometimes there are good reasons why you'd want to plot the y-axis on a log scale, then the curve wouldn't look so symmetrical anymore. And in some situations, it's the log of the value that's symmetrical rather than the base value. In this case, the time of maximum slope is halfway up, That's not always the case. And so there are a lot of different sigmoids. Very often in the world we're in, as long as you know the min, max, middle point, and the slope at the middle point, that's all you need. But there are situations in which the specific flavor of sigmoid matters. And so we'll have what are called Hill functions, which are the typical things biologists like to use. Mathematicians tend to like to use hyperbolic tangents because taking the derivative of an exponential is nice. Taking the derivative of a Hill function is less nice. And so they have slightly different symmetry properties. And so there are a lot of subtleties about sigmoids that are worth investigating. Absolutely good question. So let's actually now pull the data. We showed these data the other day. Here's our SI model of an epidemic. Here, total deaths in the UK. And I've got daily new infections in Italy, daily new infections in the United Kingdom. And to begin with, well, our orange line of I and our orange line of deaths, well, they're both orange and they're both sigmoids. So I guess that's good. So they're not totally unlike each other. I guess people here are too young to have read Hitchhiker's Guide to the Galaxy. So that joke wouldn't work. But in any case, one of the things you'll notice about the sigmoid in total deaths is that the shape of the sigmoid when it's turning on and then when it's turning off are different. And that's not true of our sigmoid here. And that becomes even more clear if I look at daily new infections. If I look at daily new infections in Italy, what I see is that there's a turn on, which doesn't look that different from the beginning of my blue curve, and there's a maximum. But then the decay of this curve is quite slow compared to the turn on. If I look at the United Kingdom, the turn on is a little bit slower, but the decay is even slower than that. Now, in both Italy and the UK, you see an increase again after they ended lockdown. In Italy, starting around July, actually it's about the same date for both, around July 14th for both. That's not something we're going to be able to model in these simple models because that represents a change in policy. But the basic shape of this curve is not symmetrical. And nothing we do to this simple SI model is going to make this curve asymmetrical. Not possible. And so we're fundamentally stuck just looking at this, what I would call semi-quantitatively. We can see that this SI model could never give us a reasonable explanation of what we're seeing. And that's actually not something you can say always about models. In general, models can prove sufficiency of hypotheses, but they can't prove necessity of hypotheses. If your model works, it's able to explain what you see, but that doesn't mean that that's how the thing that you see works. There could be something else that explains it as just as well or better, and it's an accident that what you've got works. And in biology, think that this happens as often as not, especially when you go inside the body. Very often you'll see a pathway that does something. And then classically, you'd make a knockout mouse where you got rid of gene X and gene X is in pathway Y that does Z, and the mouse is fine. And there are a number of possibilities for that. One is that you were wrong in your identification. But what typically happens is that there are redundant pathways. And in some cases, the secondary pathway isn't turned on until the primary pathway is turned off. But in more cases, they're both on all the time. And so you have two different mechanisms doing the same thing. And that shows up in a lot of biological processes. In some cases, it shows up in the form of coarse graining plus refinement. So for example, in the nervous system, There's a coarse graining that builds the initial neural connections. And then there are what are called heavy and refinement rules that do fine-grained reorganization of the nervous system. In that case, you have a two-stage process where you have different mechanisms for coarse and fine refinement. There are other ones, though, where you have two things that operate on the same scale of granularity and both do things at the same time. So we worked for many years on segmentation, on how basically the vertebrae form. There was a beautiful mathematical model of this, developed a long time ago, that we developed more. We did experiments related to that. The experiments in the model worked fine. Everybody felt, gee, this is great. And then one of our collaborators essentially knocked out all of the gene pathways and mechanisms that we had studied and showed that you got the same thing happening. And that meant that we had to go back and just realize that there was a completely unrelated way you could get the same result. And both of these things occur in your development as an embryo, or a mouse's development as an embryo. But physicists and mathematicians tend to assume that once you have one explanation, you have Occam's razor. So the simple explanation is it. Biology doesn't follow Occam's razor. Just because you have one explanation that works doesn't mean, first, that it's right, but secondly, that it could be right, but there's another one that also works, that also is true. And so that's something to remember and think about when you're doing biology. In this particular class, I don't think we're going to run into that so much, but we're actually maybe going to run into it sooner rather than later, because we're going to write down some models that will fit the experimental data that we have pretty well, but they may or may not be right. It's possible there are a lot of things that can give a sigmoid. And so if you see a sigmoid in the death rate and you fit the sigmoidal death rate, that doesn't mean the mechanistic assumptions behind that sigmoid are correct. And so one has to be a little bit cautious about that. So I want to remind you of a couple of things that we did last time. We'll have examples of these written up and so on, but this is now some coding. We talked a little bit about how to iterate over arrays in Python, and the fact that you have to put the indexes in these square brackets, and each index is in a separate square bracket, which is sometimes a little alien to people. And we'll definitely do iterating over arrays today to find things like maxima and minima. Now, NumPy has some very fancy functions that find maxima and minima in interesting ways. Whether they do exactly what you want or not is a good question, and you're free to use NumPy. And I wind up referring to Stack Overflow and NumPy documentation quite a bit sometimes, because remembering all of those NumPy functions is tricky, and remembering how they're called is also tricky. Parameter scans, a for loop in Python will more often use arange, NumPy arange than range. The need to reset our models before we run them, because otherwise they continue the previous run. How to set parameters in our model and variables. One warning, which is actually here, which is that when you overwrite a parameter value like S naught here in this model, if I change the value of S naught, it does not recalculate S. And so if I want to change S naught, and I assume S is automatically changed because of this assignment here, it won't work. I have to do that by hand. So that's something that we have to be aware of. And that actually becomes a problem when you do optimization. And so we'll run into that a little bit next week when we do optimization. So that's why you have this m.s0 is equal to m.s0 over some value, and then m.s is equal to m.s0 minus m.i. Have to do that by hand. It's a little awkward. Okay, and then using show false to stack plots, t.show to show what we plot stacked. And then if we want to do parameter outputs, say like the final value of something or something we found out iterating over our array. You can do that in a lot of ways. You can use lists and appends if you prefer them. If we're in a NumPy world, we tend to use VStack and HStack. And NumPy doesn't love an empty array. So there's this awkward command np.empty and then the size of the array. So I typically say result is npy.empty shape 02. That creates an array with no rows and 2 columns. I don't know exactly how you have two rows, 2 columns with nothing, but anyway, it worked. And then we can add our 2 columns to line by line as we build the array. And then that's plottable. There are plenty of other ways to do that as well. What this is doing here is this particular function that we've got here is looking for the time at which the number of uninfected individuals goes to half of its initial value. So it's looking for the time at which that curve decreased to half of its value and saving that. We'll have plenty of opportunity to play with those codes. Again, this is probably very familiar to people who've used Python a lot. There may be people in the room who haven't used Python so much. And so we won't use a lot of fancy Python, but these are some of the things that we'll use again and again. The only other thing that we really did last time that's hard to remember, and this is all in that Python cheat sheet and also some in the Tellurium cheat sheet, is some of the plotting commands. The plot, you can always use matplotlib if you prefer it, but the plot commands that are packaged with Tellurium have their own set of axis definitions and things like that. One thing that I find nice if you're doing parameter scans is this awkwardly named reset color cycle equal false, in which case each line in your plot will have a different color. And then labels, and that allows you to label each line. So if you have a parameter scan, you can use that. So I hope that is helpful. Again, we'll do this again, but I wanted just to remind you of those couple of things. Plot array is a function for plotting matplotlib array, NumPy arrays. It works almost the way we use the standard Tellurium plot. All right. So now let's come back after that to SIR models. The homework included this teaser on SIR models. These are models of infections, ideally where once you've been exposed, you have lifetime immunity. At least your probability of getting reinfected is very low. Coronaviruses typically do not fall in that category. You can get a coronavirus cold a lot of different times in your life. But certainly smallpox, mumps, and rubella are examples of that. If people want to do a little bit of reading and send me other good examples for SIR models in terms of viruses, that would be great. As I mentioned, this is in the Brower textbook that we have online now, chapter 2.4. This model was originally proposed, and I have not read the original paper. It'd be interesting to look at it, by Kermick and McKendrick in 1927. So it's not a new idea. Something that you see often, certainly something I experienced in my early phase of my scientific career, was that a lot of the things that we did when I was a student were going back and redoing experiments that people had done in 1820 or even 1790. And they'd come up with really interesting observations, but because they didn't have cameras and they didn't have computers, they could make qualitative observations, but they couldn't really nail things down. And so there were all these beautiful papers from, especially the last decade of the 18th century, the first 2 decades of the 19th century, which had really incredible insights, and where people said, you know, we wish we could go further with this, but we couldn't. And so a lot of beautiful mathematical modeling, Locke and Voltaire equations, also from before the Second World War. There's a lot done by hand. People did a lot of computing by hand, which was not much fun. They got very good at doing analytic approximations, because that was, even if the analytics was what we would consider messy now, it was still cheaper than having to hand iterate numerical solutions. But of course, until once computing came in, then it got all these things got a lot easier. So we're going to consider a case where individuals are susceptible, infected, or recovered with immunity. They could really be dead, but we're going to consider them as a single category. We're not going to have a separate dead category until maybe the end of this class. We're going to assume that susceptible individuals only become infected when they're exposed to people who are already infected. Recovered individuals are not infectious. Everybody who gets exposed eventually becomes infected. Everybody who's infected eventually recovers. We're going to keep our infection rate from the previous model, our SI model, so that the probability of a person being infected is number of encounters n times gamma, probability of being infected per encounter with an infected individual. I over S naught is the fraction of individuals infected in the population. The net rate is times S, the number of susceptible. And we're going to assume that recovery happens independently for each individual. And we're going to assume it works like radioactive decay, which is that your probability of a recovery is constant, and 1 over the typical time you're sick is the rate of recovery. So if you have a recovery rate mu, then you typically stay sick for 1 over mu days. So if you stay sick for a week, we're measuring everything in days, mu would be 1 over 7. If you stay sick for 2 weeks to 3 weeks, the way it is with COVID, mu would be something like 1 over 15 or 1 over 20. Okay. And so our first transition rate is n gamma over S naught, which is parameter beta, times the number infected times the number susceptible. And the second one is just mu times the number infected. This is called first order decay kinetics if you're used to chemistry. Okay. So if I write that arrow diagram in the form of differential equations, the S by dt is minus n gamma I over S naught times S. That doesn't change. The first term of I looks the same. It's the balanced term from that. And now I have minus mu I, and then dr dt is just mu I. If I add all of these up, I get 0, because the total population, which I'm here calling S naught, still is preserved. I don't have any new individuals coming in. I don't have anybody dying. So my total population is constant. Beta is the number of people that an infected person infects per day, which is n gamma S over S naught. Each infected person stays infected for 1 over mu days. And the basic reproductive number, R naught, is n gamma. That's the number of people you can infect per day. 1 infected person infected per day, divided by mu. 1 over mu is the number of days you stay sick. So the number of people I infect per day times the number of days I'm sick is the total number of people I infect if I'm infected. That's R naught. And that basic reproductive number is the headline number that you see all the time in the news these days. Who knew R naught would become such a popular name for something? I wonder if people have children named R naught. Maybe not. I don't think that's that funny, probably. We'll come back to this. There's a, I think, I'm trying to remember where this table comes from. I believe this table comes from, I believe it's in Britain, Essential Mathematical Biology. R naught is usually thought of as a number characterizing a disease, but it's got variability in a number of ways. In one case, on the one hand, R naught represent it. I mean, it's experimentally measurable in a real system. If you know how many people are infected and how many new people get infected, you know what it is up to a point. But different strains of a disease may have different R naughts. There may be more infectious and less infectious varieties of a given disease. That actually can be pretty significant because there's an evolutionary, especially diseases with rapid mutation like flu, there's a strong evolutionary selection for strain mutations that have higher R naught because they spread faster. By definition, if a disease has a higher R naught, it's more effective at spreading. So if you have a strain with lower R naught and a strain with higher R naught, you favor the higher R naught strain. Modulo certain additional complexities that are always there with evolution. People may have different social behaviors in different places, so the same disease may have different R naughts in different places. And then if the disease is carried in the air, for example, there was a lot of discussion about whether COVID would be less contagious in the summer because it wouldn't like hot weather. That seems to be true of influenza. It's not true for colds. And so we still don't know, since we haven't been through a full year with it, how true that is. So these numbers are pretty guesstimates. And they're very empirical and they're fuzzy. But flu has a typical R naught of around 4. And we'll actually see some additional tables, and you'll see that the numbers aren't always compatible from table to table. Smallpox, they give us a number 4 to 6. Smallpox, fortunately, isn't around anymore. It was amazingly contagious when it got to the New World. Wiped out something like 99.9% of the population within 100 years. So it was actually very effective at spreading itself, also very lethal. Chicken pox, very infectious. Measles, even more infectious. How many people in the room have had chicken pox? Nobody's had chicken pox? Everybody had chicken pox vaccine, so they didn't get chicken pox.
I think so.
Okay, that's interesting. Well, you'd know if you had, usually you'd know, there are people who get chicken pox and are asymptomatic, but it's not common. It's interesting because I didn't get it when I was a child. In fact, in the East Coast where I grew up, it wasn't very common. When I came to Indiana and told my doctor I'd never had chicken pox, they couldn't believe it, because essentially 100% of children in Indiana used to get chicken pox. And it's
I
an
actually
issue.
got it twice.
That's very rare.
Very rare, yeah.
Because it's considered a disease you can only get. It's a classic disease you're only supposed to get once.
Right.
Another issue with chicken pox is that it of course has nasty sequelae if you've gotten it, so shingles. And if you get it for the first time as an adult, like mumps, it can be very serious. So the fact that there was a chicken pox vaccine developed is something that was a good thing. And there's now a shingles vaccine, there's been a shingles vaccine. There's a new shingles vaccine. I got it given it last week by my doctor when I went in for my annual checkup and spent 2 days in bed because I got fairly sick from it. One of the problems with vaccines is they excite your immune system if they're working. And of course that makes you sick. So it's one of those things. So there's a lot to think about even in a simple slide like that. Okay, so the homework problem was extend our little model that we have here on the screen to include recovery. And this was a homework problem, so I assume many people have done this already. But in case you haven't, let's take a minute or two to do it together and see what changes. And did everybody do an SIR model as a homework problem? Did anybody not do an SIR model as a homework problem? Okay, I guess I have to phrase that question differently if I want an answer. Why don't we just take this little model that we have up here and make it into an SIR model? I'll do it simultaneously with you, but you can do it on your own. You certainly don't have to watch what I'm doing here. And I have a different version of it, so I can't promise that the version I'm going to write here. Why don't you try it on your own? I'm not going to talk through it. You do it, I'll do it, and we'll see whether we come up with the same thing. Okay, so that wasn't too demanding, I hope. So, well, if I look at my parameter values, clearly I need more time in my simulation. So let me go to 40 days. Did everybody get something that looked more or less like that? By the way, remember our R naught, our number of infections per infected person, n gamma over mu. N was 10, gamma was 0.1, so n gamma is 1, mu is a fifth, so n gamma over mu is 5. Basically, in this model, an infected person infects one new person per day. They stay sick for 5 days, and therefore their R naught is 5. So what happens? Well, for R naught equals 5, what can I say about this? If I look at short times, this doesn't look very different from an SI model. And it makes sense it wouldn't look different from an SI model because there are no recovereds involved. All I have are susceptible and infected individuals. But instead of my number of infecteds going up until everybody's infected, what I see is that I get a peak around the time the decrease of susceptibles is maximal. I get a peak, and then my number of infecteds tails off, and my recovereds is playing the role that my infecteds did for my SI model. And I can look at this peak, and the first thing I can say about this peak of the number of infecteds is it's not symmetrical. The shape on the leading edge is steeper than the trailing edge. And that's something that's specific to SIR models. It's going to be quite important because that mimics what we saw for the reality for COVID. The second thing that we see is that the maximum number of infected individuals in this case is about 45% of the population. And we're going to see some simulations where even though the majority of people eventually get sick, the number of people sick at any given time isn't that big. If you had one infected individual infect lots of people, but you stayed infected for a small period of time, then you might get something like that. Another thing that we'll see is that if I look carefully, it's not obvious that absolutely everybody gets infected. And that's something we're going to investigate a little bit more pretty soon. Okay, so now let us try something. We've said that the key parameter in this model is R naught, the number of people infected by an infected individual. That's the headline number. So that number is N gamma divided by mu. There's a fly flying around here. So if you see me swatting at something, it's not because I'm crazy, although I may be crazy, but because there's a fly that's buzzing around my nose. So if I were to multiply gamma by 10 and multiply by mu by 10, do I change R naught? No, I keep R naught the same. So I expect then, should things change in my simulation or not? What do you think will happen? So this is a tiny exercise, but why don't you try it? Why don't you try multiplying gamma and mu by 10, keeping R naught the same, and seeing what happens. And then for good measure, divide them both by 10 and see what happens. And run it again. So you do 3. It may be better from the point of view of seeing everything together if instead of hand changing it once and then having to keep and losing the plot, I could do something like this. Oops, I have to put it in the right place. I could do something like this where I do a reset. Well, I'll let you. Why don't you work on it on your own way? I'll do it. And by the way, the version I have online does not do it quite this way. That would be my base code to do something like that. The exercises we're going to do right now are all going to be pretty simple, but if there's an exercise where you really get stuck, I have in the Google Drive and also in Canvas, I've got all the exercises for today uploaded, so you do have those available. So if I run it, oops, I got a typo. It says you're not to trust my typing. Okay. All right. So did people can keep working, but did people who finished get something that looked something like that? Yeah, Callie. Okay. So what is this telling us? It looks like things look totally different. In one case, I can barely see what's going on. In the middle case where I made, where I divided by 10, nothing seems to happen at all. What's going on? Well, suppose that in the case where I divided by 10, I actually run my simulation for longer. Let's run it for 10 times longer. I'll have to add some data points to it. And let's do a simulation where I multiplied my rate by 10. Let's run it a little shorter. Let's see when it's done. 4 is probably a little too short, so let's run it for till 6. Make it 6. 600 and 60. Run it again. Now they all look exactly the same, almost the same. Did everybody get something like that? Were you able to do that? Not, I mean, I know you're able to do it, but I hope people have caught up. I don't want to lose people. Notice that the maximum value is the same, at least within my ability to see the difference. The final number of infecteds, of recovered, is the same. The shape of the curves is the same. So keeping R naught the same keeps the peak value of number of infected individuals the same, the final number of people who are infected the same. But it matters a lot whether I have a fast disease where people get exposed fast and get recover fast, which would be this one where everything is over in 6 days, versus one where I'm exposed and recover slowly, in which case it takes 600 days to go through the same thing. So basically, what's happening is if I change gamma and mu together, making gamma and mu bigger speeds things up. Making gamma and mu smaller slows things down. And so R naught may determine certain aspects of the epidemic. It determines the size of this peak, determines the final value of my recovered, but it doesn't determine how fast things happen. And so when you talk about changing R naught, that's only one of 2 aspects that are determinative. R naught and mu aren't independent of each other, but you can think of R naught and mu as being separate parameters.
Professor,
Yeah, go ahead.
have you done any research basically modeling the COVID epidemic with the latest R naught values for it?
So I don't typically do epidemiological models. I've taught them in a basic level for years, but only as toy models. So the answer is no. I have not done any modeling of COVID, which was attempting to be serious about it. I'd love to with you as a group. If you find a paper on modeling the epidemic that you think is a good one that we could replicate in 2 weeks, that would be fine. These simplest models, SIR models don't fit the COVID epidemic very well. SEI models do a little bit better. as I mentioned, the issue with COVID is that the key thing seems to be this period of a couple of days when you're infectious but not sick. And so having a model that includes that stage winds up being pretty important to getting to replicating the shapes of the curves that have been observed. There are models that then attempt to include things like quarantine. There are models that attempt to include that we don't mix uniformly. So there was a model, for example, of the spread of the disease in the Princess cruise ship. Wound up being very complicated because you had different cohorts. So you had elderly cruise people who were paying to be on the cruise, who had one trajectory of the infection, and then you had the staff working there who had a different, but wait staff and the people who interacted with them who had a different trajectory. And then you had the people who say worked in the boilers who had yet another trajectory. They did 3 separate submodels to predict it. In China, at least, I believe, talking to Yi, one of my old students who did some attempts to model this, that you had to have a separate model for healthcare workers, because the healthcare workers initially didn't know they had to be careful, so they were exposed to the virus at a much, much higher level than everybody else. And then they saw lots of patients for other reasons, so they spread it to people. So you had one population of people that had a very high R0, had a very high rate of infection, and then the general population that was quite different. And so those wind up then being stacked or compartmental models where you have different groups that have different interactions. So I'd be very interested. The typical numbers that are being bandied around I mean, it's complicated because when people talk about R0 as a property of the virus, but R0 is the number of people you encounter, the probability of getting infected when you encounter somebody who's infected, and divided by how long those people stay infected. Well, if you wear a mask and you're less infectious, then gamma is lower. If you socially isolate, and we'll come back to this, so you'll hear this again in a slide or two. If you socially isolate, N is smaller. If you stay home, so you're not out infecting people, effectively mu is bigger. So you're reducing the time over which you're infectious. And so social behavior or ordinances can change R0. So it's partly a property of the disease, and it's partly a property of the society and the environment it finds itself in.
Okay.
Supposedly the R0 for COVID, if you don't do anything about it, is about 4 to 6. But I think that's a bit of a guess. I think that's based on, we'll come back to that in a few minutes. I think that's based primarily on places where there wasn't any social distancing going on, where basically people let it rip. Which seems to be a pretty good approximation to Indiana University at the moment, but we'll see. Even then, and this was something that I was hearing in some online discussions by people doing this kind of modeling back in April, March and April. Even if there isn't any formal social distancing going on, when people start dying, people are more cautious. And so social behaviors change. And so one of the things that's actually it's actually non-trivial to get an R0 value out of a population curve like that. That is, at least it's not possible to separate R0 for the virus versus R0 as given by social controls. The same thing with things like smallpox. I mean, that historical number, I'm not sure where they got it from. Difficult sometimes to know how to define these things. I mean, you've probably heard of things like super spreaders. I mean, viruses are like information. You can give it to as many people as you want without running out. I mean, if you really wanted to give COVID to a lot of people and you were infected, you could go cough on large numbers of people. You're limited only by the number of people you can cough on in a day, which is quite large. In principle, if nobody was protected and you wanted maliciously to infect people, you could infect hundreds or thousands of people in a day. You could do it accidentally too, because if you have an infection that's spread by contact on surfaces, you could, suppose you're the doorknob of Ballantine Hall and you accidentally get COVID on the doorknob, and then you have 1,000 students come in for class. You could in principle infect 1,000 people easily in a day. And so one thing to remember about these things like R naught is that they're averages over large populations of numbers that are enormously variable between individuals. And so people like Alessandro Vespignani, Alessandro Flamini do a lot of work, detailed work modeling the individual transmissions and the probabilities of individual transmissions. We'll do a teeny bit of probabilistic modeling in just a little bit later in the class. Not in detail, but we'll see a little bit about probabilities. Okay, but very good question. Okay. All right. Here I picked slightly different parameter values. What was different in my parameter set from the one I have here? 10 to the 6th, I1, S0, R naught, U 1/5, and 10. Oh, here I used gamma 0.04. So let's change that. Match up. And then I have to make the times longer. Time
2,200.
Okay, so this is already showing you something interesting. What did I change? I changed gamma. That was the probability of infection per encounter. I made it smaller. And that's reducing not R naught, but it's reducing, actually I'm wrong here. I did reduce R naught. What I'm showing here is gamma 0.04, which is, let's see, 0.04 is essentially dividing this by 2. So this is an R naught of about 2.2 rather than 5. And you'll notice that if I make R naught 2.2, I can now clearly see in this that not all of the people get infected. That my epidemic sweeps through my population, but only about 75% of the population gets infected. Okay, so now let's try changing gamma, and that's where this came from. And we don't have to go through all these values of gamma, but let's try changing some gammas. Whoops, sorry. And I've suggested some values of gamma you could try. And we can do that if you have this code. We could just do it by hand to begin with. If I make gamma 0.01, takes a long time. Gamma equals 20. Everything happens very fast. And remember that R naught is the critical parameter. So why don't people try playing a little bit? I'll give you a few minutes to play with different values of gamma. And when you do that, try to remember to calculate your R naught. And I picked N is 10, mu is 1/5. So 10 divided by 1/5 is 5 times 10. So mu N over gamma is 50. So R naught is 50 times whatever value of gamma you choose. So R naught, so 0.01 times 50 would be 0.5. 0.02 times 50 would be 1. 0.04 times 50 would be 2. So I'm doing what I asked you to do. So now I should let you do it. But why don't you try playing with some of those and see what's different. Okay. So I'll give you 3 minutes, 4 minutes to play with that, if that's okay. We'll do things more automatically and set up parameter scans and things like that. But to begin with, it's helpful to play with it by hand and see what happens. One thing you may face if you have things that happen very quickly, if you look at this curve here on the bottom, you see how jaggedy it's getting. That's because my time step is too big. And so that means you have to add some extra points to your simulation to do that. So I'll give everybody a couple of minutes to play with that. And I make a comment here that you may have to adjust your time scale so you can see what's going on. Sometimes it's slow, sometimes it's fast. You know, and basically everything we're going to do for the rest of the class is going to be elaborating on this model that we just did. And when we finished with that, we basically caught up with science as of 1927. Which is not so bad, actually. I mean, quantum mechanics had been developed by 1927. Special relativity by 1927, not general relativity. So people don't get smarter. We sit on more accumulated information and experience, but we don't get smarter. As I mentioned, when I was a student reading a lot of papers from the late 18th, early 19th century, the scientists of that period were amazingly brilliant. And given the limitations that they had in terms of experimental observation capability and computation, what they were able to do was even more impressive. And they were great at observing things because they had to do everything by eye. They didn't have cameras. They didn't have any kind of automatic measuring equipment. So they had to be great at doing the kind of verbal observation that I'm asking people to do here. Okay, so as I mentioned, changing gamma is basically gamma n would be, I say here, and simulate the effects of social distancing. N really is the effect of social distancing. That's the number of encounters per day. Although I guess social distancing involves two components, reducing the number of interactions and also being further apart from people. Wearing a mask would definitely reduce gamma. And the key thing to think about here when you're looking at these would be what fraction of individuals become infected. The total number of people who become infected is ultimately the R value at the end of the simulation. When the number of infected individuals peaks, when is the maximum in your orange curve? And what's the maximum value? So for example, in this particular simulation that I did here, gamma is 0.03. So that would correspond to an R of 1.5, R naught of 1.5. What happens here? Remember that R naught by itself doesn't tell me how fast things happen, but does tell me some things that are important. That for R naught of 1.5, 600,000 out of 1 million people get infected. So 60% of my population gets infected with an R naught of 1.5. However, the maximum fraction of people infected at any time is about 5,000. So only 5% of the population is infected at any given time, but still 60% of my total population gets infected. So that's sort of discouraging because it seems like, gee, if only 5%, at most 5% of the population is infected, then the total number of people who get infected shouldn't be that big, but it still is. And the time scale for it is going to depend on the value of mu, the recovery time. Here, the one that the default one was the first one. So here, if I assume that people stay sick for 5 days, and R is 1.5, my epidemic takes 125 days to reach its maximum, and it's over after 200 days. Okay? So here were a bunch of different plots, change in gamma. In this case, I kept the time scale the same. So for small values of gamma, for R just above 1, the infection is just beginning to take off after 400 days. For R equals 25 down here in the right, bottom right, the infection's over after 3 days. Clearly no real infection is going to be over after 3 days. So it's not possible that you are sick for 5 days and you have an R naught of 25. Although we did see, which was the one that had the R naught that was very high in our table? Measles had a very high R naught. So influenza had an R naught of about 2.5, so it would be here. COVID has got an R naught of about 5, so it'd be about here. Smallpox and some of these other diseases are higher. There are a few diseases that are epidemics, but still lower R naught. So a lot of things can be seen already from this. If R naught is less than or equal to 1, you don't get any infection at all. There's no spread of the epidemic. For R naught equal to about 1.4, half the people become infected before the epidemic is over. That means that each infected person infects only 1.5 additional people. Doesn't seem like a lot. The epidemic will infect half the population. And you'll see they'll see measures in Europe, especially where they locked down and unlocked. And they'll say if the R naught goes above 1, then we have to lock down again. But this is telling you is the R naught doesn't have to go very high above 1 to get everybody sick. An R naught of 2.5 will get 80% of your population infected. So you really have to keep it at or just above 1. 1.1 is already high. Looks like a small variation on 1, but it's actually quite high. If R naught is just above 1, the epidemic spreads very, very slowly. See that here. And that's also true that for R naught just around 1, small changes in R1 make big changes in the total number of people who are infected. And so people will often look at numbers like R naught minus 1, which is really diagnostic, rather than R naught equals 1, because then small changes make more sense. Going from an R naught of 1.1 to 1.2 looks like a very small percentage change. But if you subtract 1, you're going from 0.1 to 0.2, you're doubling. And so really it's R naught minus 1 that matters. And we'll come back to that a bit later. Okay. So we can do a little bit of mathematics, not very much, but a little bit of mathematics. Let's think about what's happening when the infection is just getting started. And Josh, you're going to be on call in just a minute on this, just after the break. When the infection is just getting started, almost everybody is susceptible. We'll assume it's a new infection, so there are no people in the population who are resistant to begin with. So S over S0 is almost 1. So let's look at di by dt. That's R naught S over S0 minus 1. That's a rewrite. We have n gamma over S0 times S minus mu times I. That's our new infection rate. Remember, R naught is n gamma over mu. So I'm going to write this as R naught. Pull the mu outside. I get R naught S over S0 minus 1. Is my rate of new infections times mu. Now it's clear why when I change mu, things get faster or slower. If I multiply mu by 10, everything happens 10 times faster. So actually writing it this way is probably clearer than the way I wrote it at the beginning. At the beginning, S over S0 is approximately 1. Almost everybody's susceptible. And so my rate of new infections is R naught minus 1 times mu. So this is just di by dt is approximately R naught minus 1 mu times I. That's one of those simple differential equations people have to have in their bones. That's an exponential, which is the initial number of infected times e to the R naught minus 1 mu t. Now you see why R naught minus 1 is so important. The rate of exponential increase of that curve that we saw at the beginning of our infections in England and Italy is R naught minus 1 times mu. Equivalently, we could write that as n gamma minus mu. Okay. So one thing that's interesting about this is that the rate of infection early on, which is the first thing you see when you have a new infection, what happens when epidemiologists get together when there's a new infection? The first thing they say, what is R naught for our infection? They say, well, look at the curve of new infections. We see this rapidly increasing curve. And you say, well, we see this rapidly increasing curve. What's R naught? Can you tell what R naught is from the rate of increase at the beginning? The rate of increase is R naught minus 1 times mu. You can measure R naught minus 1 times mu, but you can't measure R naught independently because you don't know what mu is. Until you know what the recovery time is, or the time over mu is really how long people, 1 over mu is really how long people stay infectious, but you don't know. Until you know that, you don't know what R naught is. And so there was a lot of work done early on trying to calculate R naught from these accelerating curves. The answer is you can't do it. And since the final number of people infected depends only on R naught, people trying to estimate what the final infection is going to be by looking at the beginning, you cannot do it. You cannot estimate the final number infected by looking at the early number of infection, the rate of infection. But of course, that's what people want. People want to know as soon as possible how many people are going to get sick. And that early infection number does not tell you that. And so there were all sorts of nutty estimates of how many people are going to get sick based on this early data, which doesn't give you the information to determine. So that's actually a pretty important result for a little bit of simple mathematics. The rate of growth of the early epidemic doesn't tell us about R naught independently. And that means it doesn't tell us how many people are finally going to be infected. And so trying to predict from this period here in March, trying to predict how many people would be infected in December, you can't do it. Once you know mu, the recovery time, and R naught from other measurements, then maybe you can do it. But you cannot do it by just looking at the population data at the beginning. I think that's rather important to drill home because the epidemiologists forgot that. They really did. There were dozens and dozens and dozens of papers published on this that claimed that you could predict it. I was on a lot of conference calls with very irate mathematicians explaining to epidemiologists who should know better that they couldn't, you can't get blood out of a stone. If you have R naught minus 1 times mu, and that's all you have, you cannot get R naught. You have to have something else. On the other hand, let's look at the other end of the infection when things are dying down here at these late times. If the infection is nearly ended, and actually this isn't quite right here because there's still going to be some susceptible people. If the infection is nearly ended and everybody's recovered, and so I'm going to assume now that almost everybody got sick, we can get a rough estimate of the recovery rate. If S over S0 is very small compared to 1, then di by dt is minus mu I, and that means I goes like e to the minus mu t. And that means that the decay rate here on the trailing edge of this goes like e to the minus mu. So the exponential decay rate is approximately mu. That's not a great estimate if R naught is small. If R naught's big, it's a good estimate. And so the picture I have here on the right is not a very good approximation for this.
Right, because the assumption is that S goes to 0. That's when your estimation is a bit.
Right. That's right.
Otherwise, it's not a good approximation.
Now, so if R naught is 5, almost everybody gets infected, then it's a good approximation. And we're going to run into that in a minute. But this means that we could get at least a very rough idea of what mu is. And once we have mu, we can get a rough idea of what R naught is. And so this is something that I did not try in advance. And I'd like to try to do it now. So let's take a break. Josh, do you have those data sets available?
I do, yeah. I can show people how to upload them to NanoHub.
Okay, well, I get, or NanoHub, or they could do it on their local machine.
Right. I was just how to display them.
Right. Yeah. Do you want me to screen share it to you to do that?
Yeah, I can do that. Let's take
okay.
5 to 10 minute break, and then we can.
Okay, so we're at the middle of class, so let's take a few minutes of a 5-minute break. Let's meet back at 6:40. Make it an 8-minute break. And Josh, I'll let you screen share. And what I want to do is basically what we'll do is we'll plot this. All we'll do is we will plot these data set on a semi-log plot. So we will plot these data on a semi-log plot. We will measure the slope on the uphill side and the downhill side and use those slopes to see whether we can get an approximation for mu and R naught. Now, in reality, we know that not everybody in Italy got infected, and therefore the assumption that there were no susceptibles going on later was probably pretty crappy, except that everybody really did lock down in Italy. So the number of people who were available to get infected once the lockdown happened was quite small. So the number of new infections really went down. And so what we are seeing here is really clearance rate due to recovery. Okay, so let's try try that. The recovery time for COVID is 2 to 3 weeks, which means abuse should be somewhere around 0.05, and R naught's believed to be between 2 and 6. Let's see if it works. And as I mentioned, and we're in break, so I don't know if anybody's still there to listen. As I mentioned, I haven't tried this, so let's see what we get. Josh, when you're ready to screen share, let me know. And I think what I'd do is you could pull it into Excel, you could pull it into anything you like, just plot it on a semi-log axis and do the linear. We can even measure the slope by hand with a ruler if we like. But I'll leave this up on the screen until you're ready, okay? I didn't even check to see how exponential those two curves are. Plotting it on a log scale is a good idea.
We'll see how they look like. Okay, I can show.
Okay, I think officially we have 2 minutes till.
Okay, then yeah, okay, that's fine.
But if you're ready to screen share, I can transfer the screen share to you.
Yep.
Let me just check.
Just 1 second. Yeah, 1 second.
Okay, so you should be able to share now. Okay. I thought you said you had the data set uploaded already?
I do. Yeah, I'm just trying to show what I got it from.
Oh, great. That's good. Perfect. Okay.
But I never looked at it here. Like I never. Yeah.
Okay. Well, we're back
Show.
on. So Josh, take it away.
Yep. So what are we showing? What we're showing here is a resource from Johns Hopkins University. They have a repository where they are keeping track of infections around the globe, just pretty much as other places are. There is Odometer is another one that's also been tracking, and you can have access to at least you can see the plots, you can see the curves quite easily. But in the only place that I was able to find data that I can actually download and use it's from this site. I'm gonna share the link here on the chat if people are interested in playing with it by themselves. You can have access to their repository, their databases, and then you can download the data from there. So in the Google Drive, I've uploaded a couple of different data sets from 5 different places: New Zealand, China, Spain, New York, and Italy. And then we can use that just to see how the curve of the daily new infections is occurring, and use that to estimate a couple of the parameters in the SIR model. And eventually, later on, we will try to fit those parameters as well. So you can just upload all of those data sets. I'm just gonna do it for illustrative purposes. I have uploaded already the Italy data. I can upload China, New York, New Zealand, and Spain. So I have them all uploaded into NanoHub. In my Tellurium notebook, I imported NumPy and imported Matplotlib just for plotting. It's nothing too complicated. In this case, I am importing the data from Italy. This is just an import function. And this is the daily new cases. And then this data is given in days. So each data point corresponds to a different date. So I can just measure the number of days by measuring the length of this array. And then I'm just plotting here Italy, the curve for the new cases in Italy. I can do the same for other places. Let's move the time.
People seeing that data set, I'm not sure I'm finding it. Can you show us where it is again, please?
Yep. I think I posted the link on the chat, but again, and if I'm going too fast, just let me know.
Okay, got it. Thank you.
So have people used Matplotlib before? If not, I can just, because I didn't do anything too complicated, but I can walk you through what I did. It's really fast, it's really easy. So as I was mentioning, gen from text is a NumPy function that loads a file and then it generates an array based on this file. Depending on how the data is stored, you might need to pass on more options. In this case, it was just a one-dimensional array divided by commas. So this is what this is stating. I'm counting the number of days by counting how much data points I have in my array, and then the Matplotlib function is just plot my days against my new cases. And now I can do something a little bit more fancy. We can put them all together. Let's do Spain. So now you can compare Italy and Spain in terms of daily new cases, but this is since this data started being recorded, so it's not necessarily synchronic. They are not necessarily occurring at the same time. It's occurring since the data was start being recorded for each of the places. But it turns out that the data is recorded since the same day for all of them. So we can use this as a nice comparison of not just who got more infection cases, but also who got them earlier and who cleared it out faster. Then let's compare New Zealand. I don't need this. I can use the same. So yeah, New Zealand. I think the New Zealand data that I uploaded has the New Zealand data that I uploaded has also the number of number of deaths per days. So that's why I'm selecting the first row, because that's just that's the number of deaths. So that is the number of infections in New Zealand. So you can see, you can now compare. We sort of like know this by what we heard about in the news. Italy got a pretty bad infection early on. It was kind of like followed by Spain. It got worse in Spain, and New Zealand got a little bit of a bump here. We also know this was recorded for 3 months, 3-4 months, but we know that there is a second wave for all of these curves, especially Spain. But we cut it off just to get the first wave, so we can estimate the parameters from the first wave, because the SIR model that we have doesn't necessarily produce. It's not going to produce a second wave. So yeah, this is just how to upload the data. And I'm just gonna post this code here in the chat. And James, I guess I can give it back to you.
Well, let me just.
Oh, you also you said you wanted to plot in semi-log scale, right?
Yep.
So to do that, that means that my Y scale is gonna be log. So I can see now it's a little bit faster than exponential there. So it's gonna be, you have to estimate that parameter here, but this one is quite linear, so you can estimate the decay parameter from here. It's about 10 and 60 days. 10 around 80 days. Do you get that, James?
I'm still trying to get your code to work. Why don't you check with everybody to see if they're able to?
So have other people been able to plot this data by themselves?
You don't have to use that. You don't have to upload it to Tellurium. You could do it in Excel or something else too, if you want.
Right. Once you have the file, you can use your favorite plotting software. I find this one particularly useful because all I did was just 3 lines of code. Really. At least for me, it's a little bit more difficult to use Excel because I'm not used to it, but I know a lot of people use it as well. But the idea is that once we have these curves, then we can estimate some of these parameters by looking at them.
Okay, well, I at least got one of them working. So now let's see. Grab all your text. Okay. So now how do I get my log scale on the plot?
You want
Okay, great. All right. So let's turn it over to people. Are people able to get, were able to get something that looked like what they were expecting?
I guess, and for this particular case, since you guys are gonna try to estimate these parameters from looking at the curves, having the grid helps.
So I have a question.
Yep.
You know where I put the text files in order to see them? Because I uploaded them to the Jupyter NanoHub notebook, but
Right.
it doesn't seem like the my code can see it.
So
Worked for me.
So, right, once I am in, let's say, my notebook, it could be, this is the Tellurium application, but even if you're using just the Jupyter application, you click on File, you click on Open, right?
Mhm.
And then you hit on Upload.
Mhm.
And then once you upload it, you have to hit Upload.
Mhm.
And that should make it available for you. Now you can use it in your, now you can reference it.
I guess the one possibility is if you're using a Tellurium notebook, you opened in a different session, then it may be in a different root directory, in a different local directory. So what I would do is go to File and do a new notebook,
Yeah.
and then do the upload from there, and then type your text into that new window to make sure that you're referencing.
Oh
You
yeah,
can move files around. You could move files around using all the Linux commands for file CD and ls and mv, but then you have to it's a Linux directory, so you have to find the files.
right.
If you open a new notebook and then upload from that, do an open from there, then that notebook will be pointed to that directory where you uploaded it, and so it should work. I have to remind, how do you fix the Y? Is it Y scale?
Yep.
I never remember they're different in no, set Y scale. Is it set Y scale? Because we also need to limit the Y scale on this. Do you remember? Can you give us the Y scale command? Because I'm not a matplotlib person. Well, we want log. But we want to set. No, we want to set the range. so that we can see the range. So we want to set
So
the
what?
Y range
So
from
right.
100
So the way you do
to
it is by Y limb, and then you
Y
specify the
limb.
range.
Y limb. Okay. There we go. Okay, fine.
What range do you want?
Well, 100 to 10,000 is good. And then, as you say, we need to do a grid. Grid. Okay. Not, we need a.
Right, and then if you wanna, let's say, cut the on the x-axis, you can do the same with the Y limb. And let's say you wanna see just the part going up. That's about from 0 to 60 days.
Okay, I got it to work.
Looks like from 20 to 60 would be good for the
up part.
X. Yeah.
So that's the up part. It's actually like around 55 for Italy.
So everybody try see what you can get. What's the slope for the upslope? It's it goes from 10 to the 2 to the 10 to the 3 between, let's see, 27 days to 37 days. So in 10 days, it goes up by a factor of 10. So upslope.
Right, but the slope is changing a little bit, especially at the end, at the upper part here. So you might wanna do 50 for Italy, and then you can, yeah.
And the second one, the orange curve,
Which is Spain.
And then 10 days for a factor of 10 for Italy, because the earlier part is more accurate, because that's when you don't have so much. So the earlier part is better. And for Spain, it's from 37 to about 45. So about 8 days. 8 days for tenfold for Spain. Okay, and now the downslope is the one that's supposed to be diagnostic for mu. So let's get mu first. So let's do mu. So we'll start at 60. Are you doing this? Because I'm not screen sharing.
Yeah,
so.
I am showing it. So now from 60 to the end, that you can type just 60 to none. I'm gonna keep sharing the code as I update it.
So the downslope that I get is that you go down by a factor of a little less than 10 in 40 days. Is that about right? You actually go down, see, you start at 10.
Well, it's
20, 30, 40, 50. You go down from 50 to, you go down by factor 5, Italy.
Right.
Divide by 5 over 40 days.
Yeah.
And Spain is orange. And so that starts at 80. So divide by 8 over 40 days. And so we need the logarithm. We need, so
just so people understand what we are doing here, we're just measuring how fast what is the slope of this line,
right.
because that's gonna tell us what mu is. And then using the data that we collected before, we can estimate what the up rate is to determine what R naught is. So this is a very, very crude approximation, but it should give us an idea of what those values are based on the data that we have.
Mu should be log of the slope.
Right.
So the log of the ratio divided by 40. So log of, what's log of 5?
$1.6.
1.6 over 40 for mu Italy. I said 5, that wasn't, yeah. Log of, yeah, log of 5 for Italy. Mu equals log 5 over 40. Spain, mu equals log 8 over 40. So I need those two. Log 5 over 40 is what?
You want the log of 5 over 40 or the log of
Log
of 5?
Log of 5 divided by 40.
So it's are you seeing my screen? $0.04.
All right, so 1 over, so it's actually 40 over log 5 is reciprocal. So for Italy, we get 65th log mu of 1 over 60. That right? Log 5 over 40. And 8 would be log 8 over 40.
It's log 10.
Oh, I need a natural log, so that's why.
So so the reason we're saying we're taking the reason we are doing this is because this is this is in log scale, and we're assuming this is around 5. I mean, it's a little bit more. It's like around 6, but it goes from, let's say, 5 to, it goes down by 5 in approximately 40 days, which is a very.
So, well, but so the reciprocal of that is how long the disease lasts.
Right.
So the duration of the disease should be given by the downslope, which is 40 divided by natural log of 5, which says that the disease lasts about 24 days, which is 3 weeks, which is right.
Right.
So for Italy,
So,
it's telling you the calculated duration of the disease is 24 days. And for Spain, it would be divided by 8, 20 days. So that's actually not bad. Believe it or not, we got a reasonable estimate from you.
so what you're estimating is the amount of time that an infected person is infectious, right?
All right. Now, can you do the same thing on the upslope?
Right.
Let's look at that.
So, right. I just wanted to make sure that people understood what you were doing.
Well, I assume you're doing it because I can't see your screen and my calculator at the same time.
So I'm trying to follow, but I wasn't following. Like, so if you come back to my screen, we can show what.
Right.
And maybe you can draw on the screen.
Okay, good. So what we want to do here is we want to find out what this slope is. Okay. Now remember that slope is on a log scale. So once we get that slope, what we have is the following. The number of infections goes like e to the minus mu times t. And so if the number of infections went down by a factor of 8 over this period of time, then we'd say that e to the minus mu times over, it was 40 days, over 40 days equals 1/8. Okay. So now to get mu, I take the log of both sides. That means minus mu times 40 is equal to log of 1/8. Or mu equals, and I said, is equal to log of 8 divided by 40. Okay. And the duration of the disease is 1/mu. Which is 20. That was, I guess that was, 1/8 was Spain, sorry. 1/5 was Italy. So just change, sure, okay. That's fine. And so the duration of the illness is about 3 weeks, which is about right. Italy was a little bit bigger, log 5/40. If you just change, okay, yeah, that's great. 24 days. So that's actually pretty good estimate.
So I'm gonna share this code with you guys.
And let's do the same thing on the upslope.
I guess my question is, you said 1/8 because you started 8 here,
Right.
and then 40 days you went
Yeah.
from 8 to around here.
Yeah.
And then you said this is 5, but it's about 6, so it's actually closer. Right.
Yeah, but 5 it is a little higher at the end. So.
Right. It's a little bit higher here. Yep.
We're not trying to get it, but that's not a bad number.
Right.
So let's look at the beginning. Say 0 to. All right, and now let's look from day 25 to day. Let's pick it when it went over 10. So 25 to day 35.
25 to day 35.
Okay, so it went up by a factor of 10 in, actually not quite 10. How many?
It's like 7 or 8.
A factor of 7 over how many days? Started at, what do you?
That's about
28.
27 to 35.
Okay, so 8 days. So we have to copy the code that we just wrote, except change the times.
Right. So this is not gonna be mu now, though.
No, right. This is now growth. Let's just call it growth.
And this is Italy. And then this is about 8 on 8 days. So this it's not that now the duration, but it's
No, now just let's get the growth one. So growth, let's just get growth.
so it's this value here.
And now the equation that you need, and I'll type it in the chat. The equation that you need for the growth is that the growth rate equivalent to mu is equal to R naught minus 1 times mu. So if you've measured rate, what we need is that R naught is equal to R naught equal to rate divided by mu plus 1.
$7.46.
What about for Spain? Can you repeat it for Spain? Let's do
Yep.
the same.
So we're estimating that the R naught in Italy was 7.46. Let's do the same for Spain.
We'll have to replot the graph to get
Right.
the values for Spain.
Right. For Spain, I don't remember the curve exactly, so let's come back here. See
I
how
don't
they
know if this is fun for people or painful, but it's actually sort of interesting that you could do this.
it's
35 to 50, I'd say.
35 to 50.
Okay, so you go up by a factor of, let's do exactly 10. A factor of 10 between 36, 37 and 44. So 10 over 7 days.
10 over 7 days.
And I guess I have to change it to Spain.
And then
Now, whoever asked the question, did we ever do this with real data, is probably regretting it. R naught is 9.
right.
That's actually pretty good. In other words, those are not crazy numbers. In other words, we're within a factor of 2. We're within a factor of 2 on the actual duration of the disease, and the actual R naught. It's not unreasonable to assume that early on in this disease, when people weren't doing any social distancing and didn't know what was going on, that R naught was higher than it is now by a factor of 2. So actually, our estimates worked really well.
Right. So I guess I have the question whether people understood how we were looking at the lines and measuring the slope. Was that clear? Because we went over it a little bit fast, especially at the end.
I'm slightly confused.
Okay, so let's go back to the whole curve here, right? So this is the whole. Let's even go back just a little bit more. So these are the daily new cases for Italy and Spain. And James was explaining before that you can get estimates of R0 if you look at what's happening at the beginning of the curve, but you also need you also need mu, which tells you how the long tail of the curve goes down. So what we're trying to do is to estimate R0 by looking at the slope at the beginning and also measuring the slope of the downside of the curve, right? So to do that, we first started by looking at the downside of the curve. That's when we looked from 60 to the end. And we plotted them in a log scale. So we can because that is decaying exponentially, so we can estimate the decay rate by determining the slope of these curves. The way we determine the slope of these curves is that we looked at the beginning. It's a very approximate. That's what it's an approximation. We looked at the beginning of the curve here, and then we looked what happened after 40 days, and we see that it goes down by a factor of, in this case, around 8, right? Because let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8. It's an approximation. It goes down by a factor of 8 over 40 days. And this is how we determine what mu was for Spain and Italy. Right. So as James we need to know mu to be able to estimate R0. And once we have determined mu, then we can look at what happens at the beginning of the curve, and then estimate the slope of that curve to calculate mu. So to do that, we looked again at the whole curve, and now we looked at them at the declining end, but now we're gonna look at the upside, and we wanted at the beginning rather than at the end, because it's that's what James was explaining in his slide, that the approximation works at the beginning of the upside. So to do that, we looked at they sort of like have different scales here, so we looked at them independently. So if we looked at Italy, we looked in this range of, let's say this is about 25 to 35. And now we estimated the slope of this curve, which is, it goes up by a factor of 8 over approximately 8 days. So that's what we have here. That's the slope of that curve. And then we can estimate R0 now by dividing the slope of this curve by mu plus 1, which is given by the expression that James is given here.
And people read the notes that
Right. So that explains how we get from the slopes at the beginning and the slope at the end to be able to estimate R0. And we repeated the same for Spain.
But unfortunately, as you see, you can't get R naught until you've got the downslope. So basically, until the epidemic is over, you can't tell what R naught was. And so that's sort of a critical result. So Josh, if you could make that code available, save that, make it available for people, I think that would be great.
Right.
We can save that and download it as a Jupyter notebook for everybody.
Right.
And maybe type up a slide explaining the exponentials for people.
Mm-hmm.
So
I can definitely do that.
So again, I think I understand it's a bit of a leap of faith to try to do these things together, but and again, you could even if we had this on if we were in person, I would have printed this out on a piece of paper and we could have used a ruler to measure these things. But
right, we're measuring by eye here,
right,
because it's an approximation. We're not doing right. We're not taking policy decisions based on these estimates.
But we actually got the numbers pretty much right.
Yeah,
which is
they're very close.
Pretty impressive.
Mm-hmm.
It means you don't really even need an SCIR model. An SCIR model is pretty much good enough, at least to get those numbers. Okay. Any more questions? I understand that may have been a bit of a rush, but it's. I promise you, there's no exam in which you're going to have to know that. On the other hand, I would ask people to try doing that for one of the other countries at home. So in the homework, we'll ask you to pull a data set, and Josh will type up more detail. Pull a data set or use one of the extra data sets we didn't analyze. Measure the slopes any way you like. Again, you could use Excel or your eye, whatever, and then calculate these very simple things and see what the R naught and the mu are. And I promise you that at least at the beginning of this epidemic, people weren't doing things that were much more complicated than that when they were actually doing the projections of how many people were going to die.
Have anyone looked at actual estimates of R naught with coronavirus?
Well, as I say, I think the current best estimate is that R naught's between 2 and 6. So we maybe are a factor of 2 large, but that's not bad. And the recovery time we know is about 3 weeks.
Right.
So our mu value is spot on, and our R naught is a little big, but not crazy.
Okay. I'm gonna return to you, James. But if anyone has questions about this, feel free to email me. I'll make this code available to everyone as well.
Okay. So with that digression, which wasn't really a digression. In fact, I'd say at some level, doing that is probably more important than the mathematics we're doing, because that's actually taking real data that you could get from the real world and doing something that gives you some meaning out of it. In a sense, very simple calculation, but I understand it's not one that is automatic. So we actually got better numbers than I expected. So now let's come back to a little bit of math. You could ask the question, when did epidemics spread? And the answer actually is clearer in the picture that I had before here, this one, which is the rate of increase. The epidemic spreads when the number of people being infected is positive. You have more new infections than you have old infections. And so if DI by DT is positive, the infection is the epidemic spreading. And the epidemic is spreading if R naught times S over S naught minus 1 times mu is positive. So that means in particular R naught S over S naught is the fraction of people who can get infected. if R dot times S over S dot minus 1 is greater than 0, equivalently, that's R dot is bigger than S dot over S. S dot over S is 1 over the fraction that are susceptible. So the disease will spread until the number of people who are infectable has gone down, so that S over S, S dot over S, the fraction, 1 over fraction of people infectable is less than R dot. If you're in an existing disease, and half of the people are already immune, either because they've had it already or because they've been vaccinated, then S over S dot, S dot over S is 2, 1 over a half, it is 1 over 2, is 2. That means the disease will only spread if R dot's greater than 2. If you're immunologically naive for new disease like COVID, initially S over S dot is 1. So the reciprocal of that's 1, which means that the disease spreads no matter what, as long as R dot's bigger than 1, which it has to be for any disease to spread. And it will stay spreading until the fraction susceptible is less than 1 over R naught. So what was our value of R naught that we calculated? 8? Was it 8, Josh?
Yeah, it was the average was 8. Yep.
8. So 1 over R naught means that our fraction susceptible has to be less than 1/8. That means that, assuming that that R naught is right, this disease, and there's no vaccine, this disease will spread until 7/8 of the population has had it. Okay. And that's called herd immunity. If the fraction of people who are unsusceptible is bigger than 1 over R naught, then you have herd immunity. Unfortunately, if R naught is 7 or 8, that means that almost everybody has to have had it. If the disease has if R naught is 2, like for influenza, then the disease stops spreading when half the people have had it. But for a disease that has a high R naught, herd immunity doesn't work very well. Okay. Another thing that we can estimate, and I'm not going to do the calculation for you, but you can look it up, it's in Brower, is how many people, what's the fraction of people who get infected at the end, at the very end. That's the value of this green curve on the right-hand side here in this picture that I did before. And you'll notice that that depends on R naught, but didn't depend on mu. It happens to be analytically 1 minus 1 plus log R naught over R naught. You can actually calculate that by integrating the equations by parts. I'm not going to do it for you. You'll take it on faith, but we will check that whether that works or not. Another thing to ask is what fraction of people, I'm sorry, I said at the end, excuse me, that was exactly wrong. This is now actually said the maximum value of our peak. So 1 minus 1 plus log R naught over R naught is the maximum of the peak. That's the maximum fraction infected at any given time. Okay. If I want to know what fraction of people are infected at the end, that's a slightly harder problem. The fraction infected, that is this green position here, is given by an implicit equation. R final is equal to 1 minus e to the minus R naught times R final. That's a simpler looking equation, but you'll notice R final is on both sides of it. That makes what's called a transcendental equation, means it doesn't have a closed form analytic solution. If you have a symbolic manipulator like Mathematica, it can give you a pretty good approximation to it if you want it. the other thing we could do is we could solve it numerically. R final equals 1 minus e to the minus r naught r final is equivalent to saying 0 is equal to 1 minus. Have people done that? Have people tried to solve equations this way? This is a standard numerical technique. And it's actually a nice homework problem. There are a lot of nice homework problems. I'm not going to expect you to do all those nice homework problems and come up with a project for next week. But these are suggestions. 1 minus e to the minus r naught r final minus r final. I'm going to plot that as a function of r final for different values of r naught. And the place that this crosses the 0 axis here is r final. And I've got a little program, which we're not going to run now because we're going to run out of time, that generates this plot. And what I see here, if r naught is 1, basically nothing happens. The answer is nobody gets infected. R final is 0. If r naught is 1.2, that's orange. R final is over here about 0.3. If r naught is 1.4, R final is 0.5. Half the people get infected. If r naught is 1.6, 0.65, about 2/3 of the people get infected. So as you increase r naught above 1, the fraction of the population that gets infected goes up really fast. For r naught equals 2, there's 2, purple, brown, 80% of the population gets infected. And remember, r naught of 2 is actually a very low transmissivity disease. Influenza is 2. Most of the diseases we looked at had r naughts of 4, 5, 6. R naught 4, blue, is over here, something like 95%. Once you're above an r naught of 4, essentially everybody will get infected. Is that clear? Because that's an important concept. I want to make sure that that point comes across. And so this plot is again telling you this position of where this line hits this axis is telling you what is the final fraction of the population that will be infected for a different value of r naught. And remember, this is assuming that once you're infected, you never get infected again. So if it's a disease in which you can get infected a second time because you don't have perfect immunity, the results are going to be worse rather than better. And we've come up, our number for this disease is 8. That would push us way up here. Basically, everybody has to be infected for something like this to work. For the estimate of 4 to 6, 4 to 6 would put us still at the very rightmost edge. So to get herd immunity, you need 80%, 90% of the population to get it at minimum. Okay. So the last thing I'd like to do, because we're not going to have very much time, and some of these things, I'm not sure how. I'm not sure. I've got a lot of slides, which in a sense we can skip. Some of them we may do next week, and some we can skip. We can look at them offline. Would be to say, okay, let's do that. So now we've got an estimate, which is what the final fraction of the population should be as a function of r naught. Let's actually evaluate that. So let's now take our simulation here and let's do this as an exercise in the last few minutes of our class. Maybe I'd like to get a little bit further. So do you want, here, a show of hands, do you want to do this exercise now, or would you rather might come back to it? Because I do have a sort of a result that I wanted. Maybe we should skip ahead to the slides and then come back and see if we have time. But well, let's do this one exercise because we do need to be able to do these plots. So here's the exercise. We've got our code here that runs this simulation. We know how to change our R naught value. And now let's plot using VStack or any way you like. Let's plot the final value of R as a function of R naught. Okay. So what I want you to do is write a little loop that changes the value of R naught. And after you've changed the value of R naught, you run the simulation for a while and calculate what the final percentage of people infected is. That's R divided by the initial total population. And you stack that as a function of R naught and then plot it versus R naught. Is that clear? Does anybody have a question about that? I know if the previous part was not clear, we can at least be clear here. So why don't we try doing that together? And I gave some sample code here that helps you do it. Here I'm changing, and I changed gamma 1. So I changed my value of gamma since R was, remember, 50 times gamma. So if I want to scan R naught between 0 and 10, I need to scan gamma between 0 and 0.2. I'll do it with you, but why doesn't everybody give that a shot? I might type it. If you're following me, you'd probably be faster to do it yourself. Well, I'll just get rid of all the notation. Yeah. So that was my attempt at that exercise. Other people may have done better. So again, what I want to do is calculate the fraction of people who are infected at the end, which means the fraction of recovereds, as a function of R naught. And so I'm going to scan gamma in my simulation. I create a place to put my results, which has 2 columns in it. My gamma is a 50th of the R value I want. So I have to set gamma from 0 to 0.2 if I want to go from 0 to 10. I reset my parameters. I assign gamma from my loop. I define what my R naught is here outside. I didn't do it originally that way here. I run my simulation. I stack my results and I plot my results. People are free to ask questions about that if that's not clear. This is what we did this last time, and we'll be doing this a lot. So it's important. I understand that it might be more fun to jump ahead, but we need to be able to, but being able to do this is important because we need to do this a lot. I want to make sure everybody can do that.
Is there a reason we calculate? Oh, wait, never mind. I see now.
Why did I calculate R naught here? Or
Yeah. I was wondering why we had calculated R naught in the loop, and now I see where we use it later.
I mean, I could do it here inside. Originally in here, I did it inside of my result stack. But later on, I discovered I needed it for other things, so it's probably more convenient to have it calculated outside. I could have scanned R naught, but then I would have had to change my parameterization in my model. So I get something that looks like that. And it's really mostly interesting when R naught is nearly 1. If R naught's less than 1, nothing happens. If R naught is, we said before, we said that if above 4, essentially everybody gets infected, right? So the interesting values are between R naught, for R naught, between 1 and maybe 3 or 4. So let's just change our scan here. Instead of scanning to 0.2, we could scan to 0.1. And we get something more like that. And we could even zoom in a little bit more. And there's certainly no point in going for R naught less than 1. So we can do that. And that curve has sort of a funny shape. And if I look at this shape, I want to ask, does it make sense? In particular, does it make sense that when R naught is very small, just above 1, the rate of increase of the fraction of people infected is 0. Let me zoom in for small values. Let me make my gamma a little bit, top value gamma a little smaller. Does that curve make sense? Show of hands, how many people think that curve makes sense? If the dependence of the fraction infected is very strong for R between, say, 1.2 and 1.4, would you expect there to be no dependence when R is between 1 and 1.2? Think about what's going on. If I infect 1.1 people as opposed to 1.2 people, do I expect that nobody gets infected? Doesn't make sense. What do you think is happening? In fact, if I go back to my plot, I could even look at my plot that I did where I calculated the equilibrium value, and I could show that that's not right. What's happening here? Can somebody tell me why I'm getting the wrong answer? Is there something mathematically wrong in my code? Is there a logic error in my code? I need somebody to give me an answer. Otherwise, it'll turn into a homework problem. How long am I running my simulation for when I'm saying that I get my final value?
$200.
200 days. What did we discover when we changed R naught and R naught was very small? When R naught was 1.1, how long did our epidemic take? Took a very long time. So what's happening here is that for R naught just above 1, the epidemic takes a very long time to run through. Remember back, where did we do it? I'm sorry, I'm not going to sit there. When R naught is very small, just above 1, the epidemic takes a long time, and so 200 isn't long enough to see the end of the infection, so the estimate is off. If I make this number 2,000, then I have to add some points here. So I let the epidemic run much longer. Now I get that. So the slope is actually maximal at R naught equal 1. So if I didn't think about the convergence of my result by looking at the individual time series, I would get an estimate that for R naught between 1 and 1.2, nobody gets infected. And then the maximum sensitivity to the value of R naught was at R naught 1.5. In reality, the rate at which new people get infected is maximally increasing in R naught when R naught is just above 1. And so this is an example that it's very easy to write code that is numerically correct, that does what you think it does, and gives you the wrong answer if you don't think carefully about what a meaningful answer is. And so that is really the point here. I'm not going to go through this whole exercise on convergence, but you'll see that actually there's a big effect. If I change the duration of my simulation even a little bit, I rapidly get a wrong answer. And so it's actually quite important to make sure that even if the simulation is giving me numbers, those numbers aren't out of range, that I check that I've done what I think I did. I said I wanted the value, the fraction of people who were infected at the end of the epidemic. I didn't plot the epidemic for each value and make sure that the epidemic was over at the time I measured it. Now, tellurium actually has a function called get steady state value, which in principle runs the simulation long enough to get things to converge. And then you don't have to worry about doing it by hand, running it long enough by hand. There's a problem with that. I tried running this with get steady state value and it crashes. Because as you bring R naught closer and closer to 1, the time it takes to converge gets longer and longer and longer, and still get steady state value runs out of energy and says, it takes too long, and I crash. And it throws an error that's not informative. And so it's actually, even the code that's meant to help you doesn't help you in that case, which is why I didn't show that method. But this is the curve. And this is actually the correct curve. One thing that we could do now is approximate this transcendental function at small values and large values. And it's possible to do that. There are two approximates to that transcendental function that I said we didn't have a closed form for. If the R is small here, we can approximate it like this. That's this orange curve. If R is large, we can approximate it with this green curve. In the middle, it's a little harder. For our estimated value of for COVID of 6, we're all the way here on the right, all the way on the this green approximation is pretty good. I don't want to drag you through after 3 hours of class. I'm not going to drag you through the approximations today. Okay. Another thing that we could do was look at that maximum number infected. That one we had an analytic calculation for. To do that, we actually have to walk through the time series and find the time and the value at which we reach our maximum. I won't do that. We're out of time for today. We're running out of time. We've got another 2 minutes, I think. But we can do that. We can plot, again, as a function of R naught, the maximum fraction infected versus time. That increases as a function of R naught. Notice that it never gets, that for most reasonable values of R naught, a big fraction of the population is not infected at once. For flu, for example, with a value of 2, maybe 10% of the people have it at any given time. But that still means that a very large number of people get it overall. It just doesn't happen all at once. The time of the maximum infection decreases as R naught gets bigger. That is, the infection's faster for given value, for bigger values of R naught. In this case, we had those estimates, I max over S naught. That is the size of the maximum. And we could also use our earlier estimate, and I'm not going to go through that in detail now, to predict the time of the maximum. It scales like 1 over mu, or 1 over R naught minus 1. And if we could, and one thing which we could do if we had a little more time is plot those. That estimate, the maximum infected, the size of that little bump when we did the bump at the very beginning of class, that is actually exact. And so the maximum fraction infected is given exactly by R naught. So let's see, if R naught is 9 for COVID, you would expect that 60% of the population had it at once if you did nothing about it. That's probably not right. That's probably too high. It suggests that the actual fraction is that the actual value of R naught is a little bit lower. But even if R naught were 4, which is the estimate we saw here, you'd expect something like half of the population to be sick at the peak of the epidemic. If you had half of the population of the United States sick with COVID, and given how many of them need hospitalization, then the hospitals would collapse, which is what happened in Italy. And so the reason you want to flatten the curve is to try to reduce that maximum fraction infected. Flattening the curve doesn't reduce the total number of people who get sick, but it does reduce the maximum. And so, and you can see even for modest R naughts in a naive population, you can have a peak where a lot of people get sick at once. So that's pretty serious. The time of maximum infection was approximate. It's not perfect. It overestimates the time of maximum infection for small R naught. It underestimates it for large R naught. And that's because there's a Taylor expansion because of that transcendental function that we approximated. This is making a truncation. In the case I showed earlier, we did it for small values and large values and optimized it. Here we're actually optimizing it for intermediate values. And that's why it's a little bit off. Okay. So I think that's okay. That's where we'll stop for today. And that was a lot. I would like people to try. I understand that little fit that we did, that logarithmic fit that we did with Josh may have been too not as so easy to follow. I would like to. I will write up. We don't have, as before, we don't have the homework written up because we didn't know what we'd cover. I would like to be able to do one little homework problem on that, and I would like people to do this problem as a homework problem. But mainly, I'd like people to work on reading and getting ready for thinking about a project. I'd like to meet with people by Zoom in the next week or 10 days to help people find a project and begin to think about that. And if there's a particular, somebody brought up earlier that they had an idea of potentially of a paper that they thought we might want to look at to replicate in class, I'd be happy to do that with you. Are there any questions or comments before we break? I know it's been a relatively long afternoon, and I'm sure people are hungry. If people, how is the homework for this week? I guess asking people to look at okay, great. Okay. I think, again, if you're not going to hand in the homework, please let me know. There's one person who didn't hand in homework last week. If there's a problem that you're not going to do, let me know, just so that I know that you intentionally didn't do it instead of my thinking that. And it's okay sometimes if a problem wasn't making sense because we didn't get to it, to say, hey, I'll hand this in next week, that's all right. What I want to avoid in terms of homeworks is having people not hand in 3 weeks of homework or 4 weeks of homework in a row and then try to rush and get them all done at once. That winds up being painful for you and painful for us, but mainly for you, because it means that then you're not able to work on other things. So the homeworks are there to try to help you develop skill sets as we need them. They're not there to torture people. And so if you didn't do it by 3 weeks after the time it was due, if you didn't do it, you've already learned that material some other way. So don't worry about it too much. So we'll finish a little bit up on SIR models. I wanted to show you stochastic SIR models, so we'll do that at the beginning of next time. We'll do births and deaths in SIR models. We'll talk a little bit more about herd immunity and vaccination. And then we'll move to SEIR models. We'll try to actually fit that whole Italian curve and see what we can do with it. And then we will move on from there. Okay, thank you, everybody. Appreciate your patience, and I look forward to seeing you next week. And if you want to talk about projects and ideas before, email me and we'll set up a Zoom. And if there are any suggestions, comments, or questions about anything we can do better, let me or Josh know, and we'll do our best to accommodate. Okay, thanks everyone. Bye.
Thank you.
Thank you.
Thank you.
Thank you.
I actually have a question.
Sure.
What does R naught stand for again? I was kind of just like eyeing all the code and looking for where it was inside of the code, but I couldn't really find it.
It's not there. That's why it's always being written up as R naught equals N gamma over mu.
Mm-hmm.
Okay. So if you look at if you look at the ordinary differential equations,
Right.
what you have is the number of people that are infected per unit time per infected individual,
With
which
the
is N gamma over time, N gamma over S naught.
Mm.
And you have the rate at which you would get recovered, which is mu.
Mm-hmm.
And so what N gamma is basically how many people an infected person infects per day.
Right.
1 over mu is how many days you're sick.
Right.
So the product of N gamma and mu is you infect N gamma people per day and you're sick for 1 over mu days. So that's how many people each infected person infects, which is R naught. But that number doesn't show up directly in the equation.
That makes a lot more sense because I was thinking because N does represent the number of encounters a person has per day, and then you have the number of infections per encounter, so that would make it so that this is an infected person running around infecting other people.
Right. That's right.
And then you would see how many people he could infect while he is sick.
Exactly.
That makes a lot more sense. Yeah, that was a little confusing.
Okay, I apologize if I wasn't clear about that, and that's important, and I'll say that again. I think it was mentioned in the slides, but I should have underlined that. So that's important because you hear about R naught all the time, but then R naught isn't in the equations, and that was why that was a question I think Kali asked, why are we calculating R naught? And it's because there's no R naught anywhere here.
Right.
The things we control are gamma, which is the probability of infection per encounter, the number of people we encounter per day, how many people are infected, how fast we get better. Those are the things we control.
Mm-hmm.
The how many people an infected person infects is a result of those things.
Right.
Not a parameter. So that's an excellent question. Yeah.
One last question I had. So basically, you went over the last time when you said, basically there was some kind of the graph was moving a little bit slower, or there was like a pattern of movement within the graph that that showed the pandemic moving slower. Was that basically just because our simulation kind of made it out so that would happen?
So I'm not sure which.
It was the one question that you had where the graph, like we had the original graph of the pandemic, and then we minused 1, and then that caused the graph to change. I think it was like four
At
to
the beginning of the class, or
near the end.
Near the end.
So like that one.
So this one, okay.
Yes.
So this was a problem. This was really a computation, a problem about the issue of doing numerical computation.
Right.
And so what we did was we ran the simulation for 200 days, 200 days, and said at the end of 200 days, our people are infected. So R divided by the population is a fraction infected. And we now plot that fraction of infections after 200 days as a function of R naught. And we get this curve. And this curve is smooth and it looks well behaved. And so we'd say, okay, this is great. If R naught is between 1 and 1.1, effectively the fraction of people infected is 0. So provided we get R naught below 1.1, we don't have to worry.
Right.
and so, and people sometimes talk like that. If we get R naught down to be near 1, we're all right. Well, the problem is that when R naught is very small, but when R naught's 1.1, that what it means is that the epidemic spreads slowly through the population, but it still spreads. And so if R naught is 1.1, in the end, if I look here on the right, which is the correct curve, 1.1, in the end, 20% of my population will be infected, not 0.
Right.
And the reason for that is that I didn't wait long enough. When I tried to get my final value, I stopped at 200 days, but I have to go to 2,000 days to find out what's really happening.
Okay, that makes a lot.
Because I said arbitrarily that I was going to say that the fraction infected after 200 days was everybody, but in fact the thing is still going after 200 days. Does that make more sense now? So
Yeah,
I know I rushed that convergence argument, but I think because from the point of view of numerics and modeling, it's quite important. But from the point of view of disease, it's a comment about how to think about models, and we'll come back to convergence issues later. But I mean, suppose you take the AIDS epidemic, right? AIDS epidemic took. I mean, now with prophylaxis, I think probably the number of people living with AIDS is going down. But it took 35, 40 years, 35 years for it to reach its peak.
Right.
The number of people infected was going up for 35 years. So if you assume that the number of people infected after 200 days is the final fraction infected, you're getting a number that's way, way, way low compared to the real one.
Yeah, I think that makes a lot of sense because you mentioned something along the lines of have experts mentioning that as long as we get R naught, like making that mistake of having it go to R naughts being like 1.1, we would be fine. But even I guess even 0.1 of a difference is still a difference, and it's significant because it's going to cause something to happen. So that would still cause, the slow emergence of the eventual pandemic. And yeah, I think that makes a lot more sense.
Well, the good news that if R is 1.1, what it means is that if you make a mistake and you don't shut down and you wait at 50 more days, you're probably okay. Because the number of people infected during that 50 days isn't so large.
Right.
If R is 1.6 and you wait 50 days, it's too late. Half the population is infected. And this is the problem with the reactive responses to COVID, which is if there's a fraternity party, by the time you've infected all those people that you shut it down, it's too late because R naught is 4.
Right.
You don't have time. You don't have time to watch what happens and then respond. And so one of the ironies here is if this pandemic had been treated properly, everyone would have complained that everything was being shut down for nothing. Because in order to prevent this pandemic from happening, China, of course, has the ability to lock things down in a way we can't here. But in order to prevent this pandemic from happening, what they would have had to do was what they did in Italy before there were any cases. In other words, in Italy, they more or less locked everybody in their house for 3 months. Really locked people up for 3 months.
Right.
And it worked. The caseload went down a lot. Now it's coming back up because people are going crazy and mixing again. But they got rid of a tremendously high infection rate. Not infection rate in terms of total percentage of population, but in terms of the rate of increase. They were able to deal with it. If the United States had locked people up back in February or early March and said, okay, nobody can go outside for 3 months, we'd have 10,000 deaths, 10,000 deaths. But people would be baying for blood. They're already baying for blood, but they'd be baying for blood because they would say, you locked us up for nothing. Because of course, if you do treat an epidemic properly, there isn't an epidemic.
Right.
The problem with an R naught of 4 is that if you wait 2 weeks, the number of people who are infected is so large,
Right.
you can't control it. And so that's the issue. The timing is actually pretty important. And maybe I should have made some more slides about that. It's an important thing to think about. So you raise a good issue that from a point of view of public policy, the fact that R naught is big means that you have to react very quickly. And that makes it hard because if you want to actually suppress the thing, you have to react before it's had time to spread. It doesn't give you time, especially if you unlock, then you relock again. You have very little time before you have to relock. If things start going bad, you have to act very quickly. And since things are noisy, you don't always know that things are going bad. So that's a good point.
So what do you model a disease like the coronavirus pandemic with like a 1/14 maybe to sort of like indicate its incubation period and the idea that it can still be it can still spread those infections while during its incubation period.
Right. Well, there's some things that help you because once people are really sick, they tend to. I mean, if you have the poor people I know have had really coronavirus, like Bob Bacallao or now Gilberto. Once you're really sick, you don't go out, and so the number of people you're going to infect is not large. The problem, of course, is there's some people who could be quite infectious who don't get really sick. The people who are mildly or asymptomatic, who walk around, those are dangerous. And then the other people who are dangerous is the people. One of the big problems, and we'll come back to this when we do infection with viral host dynamics, what happens inside of individuals, is that, and this is better known for flu. So when you get sick from the flu, when you start feeling a headache, have you ever had the flu?
Yeah, I believe so.
Well, you get a high fever and a headache and you feel really awful and your muscles hurt. And that happens quite suddenly. Typically, actually, you often feel worse than the first day or two of the flu. Okay. The day you feel the symptoms start, the virus is actually more virus in your body than there is any time during the whole progression of the disease. The virus builds up by a factor of 1 million to 10 million between the time the first person coughs on you and the time you first feel sick at all. You don't have any symptoms. During that 2 days, you are happily spreading the disease because you're not sick. And so the problem with flu is that by the time you feel sick, you're actually already at or past the peak of the virus.
Oh. Yeah,
and that's pretty bad because it's very good from the virus's point of view because it means that when you're most infectious, you're feeling fine.
right.
You don't know you're sick. So
it just kind of like
sorry, you dropped out there for a second.
It just allows you to just spread more and more and continue spreading.
Right, and there's actually strong evolutionary pressure on viruses to do that. A virus that lets you feel great and go around spreading it for longer spreads more. And so if you have 2 strains of virus, one of which knocks you in bed right away, and one of which you feel great for several days, the one for which you feel great for several days actually wins. We're probably not going to do any evolutionary modeling in this class, but it's really interesting about strain selection. There's sort of a long-term thing, which is that viruses often also evolve to be less lethal if you keep spreading them once you're sick. So a disease where you keep moving around even after you're sick then if you die, you stop spreading it. So
Mhm.
there's an evolutionary factor that promotes viruses that keep you alive longer. But if you stop spreading it because once you're sick, you're so sick you're in bed, then the virus, from the point of view evolutionarily, the virus doesn't care whether you're dead or not.
Right.
Because from the virus's point of view, you're dead as soon as you stop spreading it.
Mhm.
And so the evolutionary pressure to be less lethal only happens in specific cases. There's been a lot of talk that maybe COVID was evolving to become less lethal. I don't think there's any evidence of that.
That's interesting.
There's no particular selection pressure for it to become more lethal because you're not spread after you die. It doesn't spread after you die. But because it's spread apparently mainly early, there's not much selection pressure for it to be less lethal. So these timing issues, and I'm not I'm teaching something I'm not an expert in. So
Right.
So if you told me that you found a paper where I was wrong, I would say I'm probably wrong. I'll read the paper. So we're all learning together a bit on this. So that's a good question. Is there anything else you want to talk about this evening, or is that?